Hello students, welcome to this massive open online course on advanced analytical technique. My name is Shahab Ali Asghar Nami and presently I am serving as Associate Professor of Chemistry in Department of Industrial Chemistry, Aligarh Muslim University, Aligarh. So this is week 7 of our course, and in this series of lecture we will be discussing the chromatography. We will be discussing important basic terms which we are using in our coming slides, in our coming lectures, and we also study the various chromatographic separations. So, chromatography is actually a branch of science that deals with the separation of constituents of a mixture. Have you ever wondered that whenever you write using a pen on a moist paper, then you can see that the it actually ink separates into a colorful rainbow. Similarly, have you ever wondered that how the scientists are able to detect very small quantities of a particular constituent in a given sample? That is sometimes up to a level of nanogram, sometimes up to a level of femtogram. So, the answer to these two intriguing questions is the same. That is, chromatography is the answer. Chromatography may be defined as the art of separation of different constituents of a given mixture. Actually, the separation science is regarded as the heart of chemistry. From time immemorial, humans are using different methods to separate the analytes of a given mixture. So, initially, the humans have used filtration, decantation, and a number of methods. So, it was the genius of a Russian botanist whose name was Mikhail Svet, who actually invented this technique, of separation, that actually called as chromatography. The word chromatography, in fact, is made up of two Greek words, that is chroma and graphy. This chroma, which means colors, and graphy means studies. So, actually, Mikhail Svet in 906 invented this beautiful versatile separation technique to separate different plant pigments, particularly chlorophyll, chlorophylls, and xanthophylls. So, chromatography may be defined as an analytical technique for identification, for separation, for identification, for qualitative estimation, as well as for the quantitative estimation of different components of a given mixture. Now, there are certain terms which we shall be using throughout this unit and in the coming unit also. So let us go through those basic terms. The first and the foremost term which we are using, which we'll be using here, is the stationary phase. A stationary phase may be defined as a fixed medium. It may be solid or it may be liquid immobilized on some solid support. And it is the stationary phase on which the separation occurs. Similarly, we will be using mobile phase. Mobile phase will be defined as a solute, a solvent may be defined as a solvent. This solvent may be in liquid state or sometimes it may be gaseous, by which you actually mix your compound which is to be separated, and by using the mobile phase you actually separates on the stationary phase. That is, the partition, or you can say the separation of different constituents, occurs on the stationary phase. So here we have a quick view that how actually this separation occurs. It's a typical chromatogram. You can see that here the bands, the three different colors are moving. So this space is called as the stationary space, and you keep on adding mobile phase, fresh mobile phase each time, and because of the addition of mobile phase, your different components gets separated in the form of bands. So you can see that these bands are going down. This is the column, and these bands are going down. The movement of your mobile phase is by the action of gravity, and the passing away of the mobile phase is actually called as illusion. Illusion, that is washing away. Illusion may be simply defined as the washing away or simply passing away. So the terms which we are using is the stationary phase, a fixed medium, it may be solid or it may be a liquid immobilized on a solid surface. Similarly, the mobile phase, which actually helps the solute particles to separate on the stationary phase. Then we are using the word analyte. Analyte will be defined as the component or a mixture of component which is to be separated. We have illusion, that is the passing away of the mobile phase along with the different constituents through the column, and this illusion occurs by the action of gravity. So here what happens is that the different components elute from the column at different times is because that each component interacts with the stationary phase in a different manner, and this is because of the differential migration of the different components. This illusion take place. That is what, in simple sense, you can say that the different components interact with the stationary phase differently, and each component has a different interaction in terms of strength. So greater the strength of interaction, greater will be the time it will spend with the stationary phase, and greater will be its you can say retention time. Retention time means that is the time taken by a particular you can say component with the stationary phase. So what happens is that here the basic principle of separation is the differential you can say migration rate, and this differential migration rate occurs because of the difference in the interaction of the different constituents with the stationary phase. So the separation occurs because of the differential interaction that leads to differential migration. So here the solute gets partitioned between the stationary phase and the mobile phase. Now the fundamental principle or the basic principle of the chromatography is the differential affinities. So each component interacts with the stationary phase in a different manner, and since the interactions are different, so each component is going to stay for a different time with the stationary phase, and on the basis of the difference in the staying, there is a difference in the illusion or you can say in the going away of that component from the column. That is, each molecule actually has a different interaction with the stationary phase, and because of that each component has a different retention time. Retention time is the time taken by the particular component with the stationary phase. So stronger the interaction, greater time it will have with the stationary phase, and greater the time, that is you can say greater the retention time, it is going to stay for more time, or you can say then it will elute last. Okay. So similarly, on the contrary, if the interaction is less, then the elution will be fast. Okay. So as a whole, you can define as the components gets partitioned between the stationary phase and the mobile phase. And you can say if you have a single component system, then that component will going to equilibrate between the stationary phase and the mobile phase. That is, there is an equilibrium. And if you want to uh, give this equilibrium in terms of K, then that may be defined as equilibrium of K of stationary phase upon concentration of A in the mobile phase. Similarly, this is also called as the distribution constant. And this distribution constant may be simply defined by capital K, that is Cs upon Cm, concentration of the solute in the stationary phase divided by the concentration of the solute in the mobile phase. You can also define this K as the number of moles of solute in the stationary phase divided by the volume in the stationary phase upon number of moles of solute in the mobile phase upon volume of the mobile phase. You can also define like this. So this distribution constant, which is actually different for each component, is actually the measure of the interaction with the stationary phase and the mobile phase. Now, the problem with that distribution constant that you cannot measure it directly. So in the coming slides, we will see that how we are going to quantify this important characteristic feature, that is the distribution constant. Let us look into the historical evolution, that how this technique got evolved and how different stages are there. So in 1906, it was the genius of Mikhail Sweat, the Russian botanist, who invented this technique to separate different plant pigments like chlorophyll, xanthophylls on a glass column filled with calcium carbonate. So he used actually calcium carbonate to separate chlorophyll and xanthophylls. Then comes another advancement that is called as the paper chromatography. This technique was exclusively used by the organic chemist. And here in paper chromatography, they actually use a strip of paper, and on that paper, they take the mixture which is to be separated, and they also take some authentic sample so that they can be compared. And then they put this paper in some cylinder or in some beaker with certain solvent which acts as a mobile phase. They dip it little bit, and then what happens is the solvent system rises, and this also rises, and after a certain time they show a different colors, and on the basis of color you actually identify that if there are three spots, then you can say that it's a three component system, and each component have a separate RF value that is called as the retention factor, and this RF value is characteristic for each component. So that was the advent of paper chromatography, and by using the paper chromatography, you actually identifies a particular component. You actually check the purity of the sample. So organic chemistry people use this technique to monitor their reactions also. Similarly, in 1950s, there comes a revolution, and this technique of initially the technique of elution chromatography got advanced, and it evolved as gas chromatography. And that gas chromatography is the versatile technique of separation of volatile compounds. So it was the best technique to separate volatile compounds in just a matter of few hours. You can separate a multi-component system, a multi-component mixture. But the issue was that this technique was good for separation of only the volatile components. Then comes the high performance liquid chromatography, or HPLC. Sometimes it is also called as high pressure liquid chromatography, because here the pressure you need is very much. Sometimes you need a pressure of suppose 5000 psi. This technique was versatile in the nature that you can use HPLC to separate non-volatile compounds also. You can separate the thermally labile compounds by using this HPLC. So HPLC has changed the whole scenario of separation science. Then comes the most advanced technique that is called as UHPLC, or ultra high performance liquid chromatography. So this was more advanced than HPLC, and now you can separate even femtograms of your compound. Okay, femtograms. This is highly sensitive. This is highly specific technique of separation. Then comes the LCMS, then the microchip based chromatography. That is, now you can have, instead of having using a very big instruments, now you can separate your mixture in just by using of just a chip, and you only need nanoliter of sample. So this has actually changed the whole scenario, And again, the sensitivity is very high, specificity is very much, and these techniques are fully automated in nature. So this has changed the whole aspects of separation. Now, this chromatography is not only important for the chemistry persons to identify the unknown compounds or to check the purity of samples, but they are also good for the biology people, because this chromatography can be exclusively used to separate biomolecules, to separate proteins, to separate nucleic acid, to separate peptides. And there is a specific chromatography which we are going to see, that is called as affinity chromatography in the coming slides, where you can exclusively separate your biomolecules. Then comes the pharmaceuticals. This chromatography is exclusively used in pharmaceutical uh, research or pharmaceutical analysis, because it can uh, give you an idea about the purity of your drug, about an idea about, you can do some bioequivalence studies by using this. You can actually standardize your drug by using different chromatographic techniques. Forensics nowadays, this GC or this HPLC has also gained very much uh, importance in the area of forensics. In fact, now on this is chromatography by which a traffic police person can check that whether a driver has drunk or not, by just checking the alcohol, that whether he has uh, taken some alcohol or not. Similarly, you can also check narcotics. Even nowadays, in various accidental cases and in various suicides, this is checked by using the various chromatographic techniques. That is, whether a person has consumed poison or not. Similarly, in environment, it has made a big throw. That is, now you can check the trace level pollution by using different chromatographic techniques. Similarly, in food industry, it becomes mandatory to have a proper, you can say, specification of the different constituents present in a given food item. So this chromatography is actually become a multifaceted technique, and it has found significance in almost all the branches of science. Now, why chromatography is gaining so much importance? It is because of the high sensitivity. Now you can detect femto level concentration, that is up to a level of 10 raised to the power minus 15 gram. You can understand the sensitivity, such a high sensitivity. Similarly, versatility. Uh, you can identify gases, you can identify solids, you can identify liquids, you can identify polymer material, you can identify biomolecules. Just name the compound and the answer is with the chromatography. So versatility is there. As I have already discussed, that it is a technique which can give you identification, which can give you a qualitative idea, as well as the quantification of different constituents present in a given sample. So it serves all the purpose of separation. Similarly, the size, you only just need nano levels of, or nano liters of sample, and in just such a small quantity you can check all the components. Okay, so scalability, you have seen the nano, you have seen the lower limit, and now you can see the higher limit. You can use this technique for industrial purpose also, for large scale industries also. Okay, so these features make this chromatography a versatile technique. Now, how this chromatography actually works, what are the different, what are the different, you can say, steps involved in the chromatographic separation. So initially you have to have your sample. So you must have a sample which is to be separated into its constituents. Then you have to have a certain mobile phase. It may be a liquid, it may be a gas, depending upon the nature of an analyte which is to be separated, depending upon your requirement of separation. Similarly, now after choosing the mobile phase, you have to have a stationary phase also. Then what happens is that partition occurs between the different constituents, and because of the difference in partition, they migrate differently, and because of the difference in migration, they elute at different times. So you have a visualization, and because of the illusion at different times, they appears as in the form of bands, they appears in the form of zones, peaks, because you get a chromatogram which is like this. On the x-axis you have time, and this time is generally called as retention time. Retention time. And on the y-axis you have detector response. Detector response. So you actually get this type of. This is for a two component system, for example. You have two component A and B. So each component actually comes in the form of a peak or in the form of zone, which we have seen in the previous slide. And this peak actually gives you an idea about the mobile phase, illusion of mobile phase alone. We will discuss this point. So this time up to half of this peak is called as TR of A, and this time half of this peak is called as TR of B. That is retention time of component A, TRA, retention time of component B. That is the time taken by the component to pass from the column. Okay. So detection, you can get a quantitative idea as well as a qualitative idea. That is, you can have information that how many different components are there, and if you know the number of components, it also gives you that how much each component is there in the given mixture. So you can classify the chromatographic techniques into a number of ways. You can classify on the basis of the principle of separation. On the you can classify chromatographic techniques on the type of or on the state of mobile phase used. You can also you can also classify the chromatographic techniques on the basis of the format, on the basis of shape. So on the basis of principle of separation, chromatographic techniques may be classified as adsorption chromatography, partition chromatography, ion exchange chromatography, size exclusion chromatography, and the specific and specialized affinity chromatography, which is exclusively used for the separation of biomolecules. So we are going to see each type of chromatography in detail in the coming slides. Similarly, on the basis of the state of mobile phase, we can classify the chromatography as gas chromatography, where the mobile phase is gas. We can also classify it as liquid chromatography, where the mobile phase is liquid. Similarly, on the basis of format or shape, we can classify them as column chromatography as well as the planar chromatography. We are going to study each of these in the coming slides in detail. So on the basis of principle, we can classify it into 5 categories, namely the adsorption, the partition, ion exchange, size exclusion, and the affinity. In adsorption chromatography, the principle of separation of different constituent is the differential adsorption of components on the stationary phase. That is, here the principle is the surface binding, because adsorption is a surface technique. Similarly, the partition chromatography, here the different constituents of a sample separate on the basis of the differential partitioning of components between the two immiscible liquids. Okay, we are going to see it in more detail in the coming slide. Similarly, we have ion exchange chromatography, where the principle of separation is the difference in charge. Okay, so different constituents separate on the basis of difference in charge with regard to the stationary phase. Similarly, we have size exclusion chromatography, where the principle of separation is the difference in the size of the different constituents of the mixture. Similarly, we have the affinity chromatography, which is very specific one, where your actually stationary phase acts as a ligand and it captures a specific targeted molecule in the which is coming as a analyte. Now, adsorption chromatography. Let us dwell into the mechanism. Here, the separation occurs on the basis of the adsorption of the different constituent of the analyte, and the different components get adsorbed on the surface by weak interactions. That may be van der Waal interaction, that may be hydrogen bonding, or there may be some weak electrostatic forces. Here, generally you take stationary phase as a silica gel, you take alumina, sometime you also take other stationary phases like polyvinyl benzene, polyvinyl alcohols, etc., etc., depending upon the nature of the analyte. Here you take actually the mobile phase. Mobile phase is generally you can say organic compound, organic liquids. You start from non-polar, you start from benzene, hexane, chloroform, methanol, and you keep on changing. And this type of chromatography, where you keep on changing the polarity, is sometimes also called as the gradient dilution chromatography. Okay. And on the other hand, if you are taking the solvent, or if you are have a fixed solvent system, then that type of chromatography is called as isocratic elution chromatography. And the common examples are the TLC, that is the thin layer chromatography, or column chromatography. This type of chromatography is very good for the separation of natural products, for the separation of common organic compounds, and also for checking the purity of a given sample. Then comes the partition chromatography. Here, the basic principle of separation of different components is the differential partitioning of the components between the two immiscible liquid. Here, what happens is the stationary phase is actually gets coated by a mobile phase. Okay, and now the solid is coated with a mobile phase, or you can say immobilized on that solid support, and your liquid, which is a mobile phase, and now the partitioning of different constituent occur between this stationary phase and the mobile phase, and these two liquids must always be immiscible. Okay, so here the basic principle is the partitioning of component between two immiscible liquid. So this type of chromatography is used for the separation of amino acids, for the separation of pharmaceutical drugs. Similarly, this is also suited for the separation of metabolomics. Okay, so this is about partition chromatography. Then comes the ion exchange chromatography. Here the separation occurs because of the difference in the electrostatic charges which are present in the solute, or in the mixture. Here the stationary phase contains certain charge group, and because the elutes, or the you can say your components also bear certain charge, so they opposite charge get attracted, and they, on the basis of the attraction, certain ions pass quickly while certain retain, and after some time they also pass. So this type of chromatography is very useful for separation of amino acids, for the separation of enzymes, and also for water desalination. Here we use aqueous electrolytes as the mobile phase. Then comes the size exclusion chromatography. This is also called as gel filtration chromatography. Here the stationary phase contains certain pores, components. According to their size, the sum of the components which have comparable size with the pores that are present in the stationary phase, they get trapped, while the particles which are greater than the size of that pores, they just pass through, and the particles which are bigger in size than the pores of the stationary phase takes shorter path, or you can say elute quickly. Here elution is quick, and the molecules which gets entered or get trapped, they elute later. Okay, on this basis of the difference in the elution pattern, the different components get separated, and this type of chromatography is very good for determining the molecular weight of polymers as well as for the protein fractionation. Okay, so now comes the aphoretic chromatography. This type of chromatography is very good for the separation of biomolecules. What happens is that, for example, if you have a column, if you have a column and this column is made up of, you can say, is made up of specific type of ligands. Now let us suppose they have a specific type of ligand which have this type of, stationary phase, and you have mixture which contains this type of particle, triangular, circular, and some squares. Then when you pour this mixture along with mobile phase, mixture plus mobile phase, then what happens that those which have which are square in shape, they get trapped, they get trapped, while the other one, they go as such. So here you can see that elution occurs very in a very specific manner. Now this may also be regarded as a lock key model. So here the ligand actually immobilized on a resin, and it has a specific, opening where a particular biomolecule gets trapped. So it is very specific for a specific type of separation. And here the final elution occurs by the salt gradient or by competitive binding. And this type of affinity chromatography is very good for the separation of biomolecules, for the DNA protein binding, etc., etc. So the separation, the chromatographic classification on the basis of the mobile phase. On the basis of mobile phase, you can classify, for example, if your mobile phase is exclusively, for example, is if it is exclusively a gas, then you can call it the gas chromatography. And generally in gas chromatography, the mobile phase is taken an inert gas, generally the helium, argon, and sometimes nitrogen also. So in gas chromatography, the mobile phase is always a gas, while in liquid chromatography, the mobile phase is always a liquid solvent. Okay. Similarly, we have another type of chromatography which is called as supercritical fluid chromatography or SFC. Here, the mobile phase is actually a supercritical fluid, generally supercritical carbon dioxide. So, we are going to study the gas chromatography in unit 4 after this unit. Now, the gas chromatography. It is one of the versatile technique of separation. This technique has actually made a breakthrough in the separation science. Here, the mobile phase is always an inert gas, and the use of this, the main objective of the mobile phase is to take your sample to the column where actual separation occurs. So, mobile phase only act as a carrier and it must be inert, because if it is not inert, then there are chances that it will react with the different constituents of the mixture, and that actually leads to improper separation. Similarly, in gas chromatography, you actually coat your stationary phase with certain liquid, and then the separation occurs. So GC is very useful, that is gas chromatography is very useful for the detection of environmental pollutants, for the detection of for petrochemicals, for checking the purity of drugs, etc., etc. Now the biggest advantage of using GC is that it gives you very good, well resolved peaks, and it's a very rapid techniques. But at the same time, you can only separate mixtures of limited size, of limited volume. Okay, this is one of the drawback, and this technique is only good for volatile compounds. Okay, you cannot separate non-volatile compound by using GC, because your sample is to be in the volatile state so that it can mix with the carrier gas. So if your sample is a liquid, then it is to be, initially it is to be volatilized before passing it to the main column where separation occurs in the gas chromatograph. Then comes the liquid chromatography. Here the mobile phases always are liquid, or you can also use aqueous systems, aqueous buffers you can take. Here the stationary phase may be a solid, or it may be a solid which is coated by some liquid. So paper chromatography is the best example. In paper chromatography, the it generally the paper is a cellulosic paper, so the holes of that paper contains the water, and that trapped water actually acts as the stationary phase, and the liquid, the solvent in which you dip your paper, acts as the mobile phase. So the common example is TLC, another that is the thin chromatography. This is HPLC, that is the high performance liquid chromatography. We will be studying this chromatography in detail after GC in unit 4. So this is very good for the bioactive profiling, for the pharmaceutical quality checks, and for the metabolic profiling also. Now the supercritical fluid chromatography. This is very specific technique, not commonly used, but again it has very specific applications. Here actually we take supercritical, we take carbon dioxide as the supercritical substance, and above its supercritical point, the beauty is that it acts as a gas like, and it also has some liquid like properties. So it combines with the speed of gas chromatography, and it has the selectivity of the liquid chromatography. So you can actually monitor, you can separate the thermally labile compounds by using the SFC, which you cannot separate by using simple GC. Similarly, you can separate chiral compounds using this SFC, that is supercritical fluid chromatography. Now comes the format based. You can also classify the chromatography on the basis of the format, that is whether your stationary phase is packed in a vertical column, then you call it a column chromatography because it is packed in a column. Now if the stationary phase is spread in a 2D surface, for example the paper which we have given to you, this paper contains pores, and in these pores the water is trapped, and this type of chromatography is called as the planar chromatography. Similarly, we have a capillary chromatography where the separation occurs in the microcapillaries. Get few information, simple information about column chromatography. Here the mixture is applied on a packed column, and it is the column chromatography which was the first type of chromatography used by the Michael Sweat. Actually he taken a glass column, and in that glass column he filled calcium carbonate. So calcium carbonate acted as the stationary phase, and on that stationary phase he separated the plant pigments, that is the chlorophylls, xanthophylls, etc, etc. So here the solvent flows, you actually, here you add, you have a column, and this column contains certain stationary phase, and what happens is, on this you take your mobile phase plus your mixture which is to be separated, and you just pour it, so it percolates and the sample travels by the action of gravity. Sometimes you can also put pressure also. In GC you actually use pressure, in HPLC you use pressure because that column is very tightly packed in HPLC, and you use extra pressure, sometimes up to 500 psi you need pressure, so that you can actually pump your solute along with the analyte, along with the you can say mixture where actually main separation occurs. So here the components elute at different times, and because of the difference in elution times you actually separate each component. So this is very useful for the separation of natural products, for the separation of inorganic compounds also. Now the paper chromatography, it is one of the most used type of chromatography in the laboratories, to monitor the reactions also. Here the stationary phase is again water molecules bound or trapped in the pores of the paper. Here the mobile phase, you can take any solvent, and on the basis of change of polarity you actually get a good separation. So you keep on changing the polarity, you keep on getting a good separation. So you can visualize these colored spots sometimes by a naked eye, and sometimes you have to develop these in terms of in by putting it in the chambers of iodine, where the components make reversible bond with the iodine, and they actually comes in more bright colors. You can check the purity of food colors or amino acids and various pigments by using this paper chromatography. Then the TLC, here the stationary phase is silica. Generally, this is also a laboratory technique where you use glass plates, and on glass plates you coat silica or alumina, and then you put your sample by using a capillary. Again, you have a glass slab, and on that you actually coat it with silica gel, and on that you add your mixture as a pores by using fine capillary, and then you put it in certain beaker, and in beaker, for example, here is a beaker, and in beaker you use certain mobile phase, and what you can do, you change the polarity of the polarity of mobile phase, and the spots rise, and after that you take out, and you sometimes the spots are visible in the naked eye, otherwise you can put in iodine chamber, and after a certain time the spots they gets developed, and they are more visible. So you can check the reaction, that whether reaction is going in the right direction, whether a mixture of compound is forming, or there is a single product formation. So you can check it. So you can use UV lamp, you can use iodine chamber. Sometime you can also use fluorescence tagging by adding some certain fluorescence agent, so that you can get a good fluorescent uh, peak. Now the HPLC, this is one of the most versatile technique. So here you use high pressure pumps instead of gravity alone. You actually need high pressure, because the columns here are tightly packed by the stationary phase, and in order to pump your mixture along with the mobile phase, you need high pressure pumps. So this is very highly efficient technique. It gives sharp peaks, very good quantitative idea, very reproducible result you get. Now here in HPLC you can have a number of different detector. You can use UV detector, that is ultraviolet visible detector. You can use fluorescence detector, you can use diode array detector, you can use a number of detectors depending upon the nature of sample given to you for separation. Similarly, sometimes you can also use mass spectrometer detector, and by using this MS detector, that is a mass spectrometer detector, you can also get an idea, you can also get the structural information of the different components. So you can use a number of detectors, and also you can use more than one detector at once. That is, you can use hyphenated detector, that is more than one detector. For example, you can use UV plus MS. This is very good for detecting the drugs, for checking the purity of drugs in clinical diagnosis as well as in the biomolecule profiling. So this is one of the most advanced separation technique. Now there are other special technique also for special purposes. For example, we have capillary electrophoresis. Here the principle of separation is the charge and the size, and the separation occurs in very narrow capillaries. Similarly, we can have liquid chromatography mass spectrometry. Here, that we have already discussed, you couple your HPLC equipment, that is high performance liquid chromatography equipment, with mass spectrometer, so that you can also get identification, you get a qualitative idea, you get a quantitative idea, and by using the MS you get the structural information of the different analytes, of the different, or you can say, or the different components present in the supplied mixture. Similarly, nowadays you have a very small miniaturized systems where you can check the purity of a sample in just few minutes, and you only need nanoliters of sample. You can analyze in a very small sample, and you can also check the purity of that particular sample. Now let us get a comparative idea about the various techniques and the applications which each technique gives you. For example, adsorption chromatography. Here the basis was the surface interaction. In this case, the different components of your mixture gets a surface interaction. They get adsorbed on the stationary surface, and because of the difference in the adsorption, because of the difference in adsorption strength, they gets retained for different times and they elute at different times. So a common example is TLC, and you can separate natural products by using adsorption chromatography. Similarly, you have partition chromatography, where the different components gets partitioned, and the basis of separation was the solubility. And the best example is the high pressure liquid chromatography, and you can separate different drugs, different metabolites by using HPLC. Similarly, you have ion exchange chromatography, and the separation basis was the difference in the charge. Now, a good example is the protein purification, where you actually get different positive and negative ends. So, you can, all the biotechnology laboratories actually use this ion exchange chromatography for separating different components of protein or other biomolecules. Similarly, you have ion size exclusion chromatography, where the basis of separation was the difference in the molecular size. And a good example is the gel filtration chromatography, where actually your stationary phase was a porous and it contains different pores of different sizes, and those molecules of the mixture which has comparable size to the pores, they get trapped, they get fit in, while the bigger molecules, they just elute very quickly, and after a certain time the trapped molecules also eluted and a good separation was done. Similarly, you can separate proteins and polymers by using size exclusion chromatography. Then comes the last one, which was very specific type of chromatography called as the affinity chromatography. It actually was based on a specific binding of the stationary phase with the analytes of the mixture, and it is very good. Example is immunoaffinity, and you can separate monoclonal antibodies by using affinity chromatography. It was also good for separation of proteins also. Now, what are the advantages of chromatography? It gives you high selectivity and very good sensitivity. Selectivity was very high and sensitivity was very good. For example, sometimes of the range of 10 raised to the power minus 15, depending upon the detector, in case of GC and HPLC, that which type of detector actually you are using. So on that basis, you can have selectivity as well as sensitivity. So you can separate complex mixture by using HPLC, and you need only microscopic amounts. You do not need samples in ml or in 10 ml sample you need, or 1 liter sample you just need only nanoliters of sample, that is up to a level of 10 raised to the power minus 9 liter. So you can see that in just such a small amount you can get an idea about the number of component present, and you can also get an idea that how much each component is there. So by coupling different detectors, you can also get structural information, as you have seen that by using MS detector, you also can also get a structural information of the components. Similarly, it has actually become a very important technique for almost all the branches of science wherever separation is involved, and also in industry. So there are certain limitations also of this chromatography, that in certain cases you need very costly equipment. For example, HPLC is very costly, even GC is very costly. It comes in more, a good GC with a very good sensitivity, it actually the equipment comes in 25 lakh rupees. So for such a costly equipment, you also need very specialized or very technical type of person for doing the analysis, for performing the analysis. Similarly, certain chromatographic techniques are time consuming for large scale. And there is actually nowadays we are using programmed GCs, which has actually cut short the run time. That is, skilled labor is required, for example, in GC and in HPLC, and sample preparation is very important. For example, when we will discuss the GC, then we will see that sample injection is very important, and there are different ways, there are different techniques by which we can actually introduce our sample. We have splitless injection, we have head-on injection. So depending upon the nature of the sample, we have to decide the sample injector port also. So now there are certain real world example that where HPL, where this chromatography comes for our help. So food safety, for example, for checking the melamine content, for checking the artificial dyes in food products. So HPLC is the answer to detect all these. Similarly, in forensics, for example, if certain hanging is occurred, or certain, if certain poisoning is there, so autopsy you need specialized GC for analyzing a particular body part. Similarly, in pharmaceuticals, to check the impurity, to ascertain the percent purity, you need this GC to check this. Similarly, in environment, to trace the heavy metal ion concentration, to check the pesticide residue or other insecticide. So GC can give you a very good information. Similarly, for the purification of hormones, for example, insulin, or to a certain growth factor. So by using the affinity chromatography, you can have a very good idea. You can detect to a very good sensitivity. So with this, we can have the chromatography. Now let us quickly recap and see that what we have learned today. So chromatography is actually the heart of separation science. We can classify the different chromatographic technique on the basis of principle, on the basis of mobile phase, and also on the basis of format. And we have seen that on the basis of principle, we have classified as adsorption, partition, size exclusion, partition, as well as affinity chromatography. Similarly, on the basis of mobile phase, we have classified as in the form of gas chromatography as well as liquid, and also classified the format. So this chromatography is vital for not only chemistry but for biology, medicine, of course, industry and environment. So nowadays, the technique is so advanced that miniaturization has occurred, and now we also have AI for our help. So by just by combining these versatile techniques with AI, we can have a very real time analysis of different constituents of a given mixture. So chromatography is transforming the whole landscape of separation science. So with this quote, we are finishing our uh, introductory lecture on chromatography, and in the coming lectures, we are going to see elution chromatography, we are going to see the optimization, and we are going to see more aspects of chromatography. Thank you very much. Have a nice day. Thank you.